Here we have a batch of parts that we need to turn around as soon as possible as a favor to one of our customers. To eliminate as much programming lead time as possible, our machinist Jay is going to use CAMAssist to generate the bulk of the program. Overall, CAMAssist is responsible for providing around 80% of the complete toolpath, saving Jay several hours of manual programming time, accelerating the process of delivering these parts to our customers. Our challenge with these parts is to drill the deep holes through the side of each part, whilst they are still contained within their single operation breakout frames. Typically, any hole with a length-to-diameter ratio of 10 times diameter or greater is considered a deep hole. To achieve this, we will need a 5.5mm drill with a length-to-diameter ratio of 20 times diameter. A drill this long requires a specialized deep hole drilling strategy. This is a process which requires two-stage drilling. Initially, a pilot drill is used, followed by a long series drill. Understanding this complex drilling strategy is beyond the scope of the AI right now. For the time being, this is going to be implemented into the program manually. So, let's talk a little bit about each drill. Ideally, the pilot drill should have a larger point angle than the long series drill. In this example, the pilot drill has a tip angle of 140 degrees, whilst the long series drill has a tip angle of 135 degrees. This ensures that the tip of the long series drill meets point to point with the tip of the pilot drill. The pilot drill should have a larger diameter than the long series drill by a very minimal amount. This is to allow a small amount of clearance between the cutting edges of the long series drill and the pilot hole it feeds into. The clearance between the pilot drill and long series drill is controlled by the ISO shaft tolerance applied to each drill piece. In our case, our 5.5 pilot drill has an ISO shaft limit of M7, which ensures the drill must be slightly larger than 5.5 millimeters, whilst our long series drill has an ISO shaft limit of H7, which ensures that the drill must be slightly smaller than 5.5 millimeters. Now let's talk about the drilling strategy itself. It is essential that the stubby pilot drill has minimal runout and should be checked with a dial test indicator, as this drill is responsible for drilling the pilot hole in an accurate position to be used as a guide for the much longer drill. The pilot hole is drilled to a depth of up to 2 times its diameter. Spindle speed is 14,469 RPM, with a feed per revolution of 0.25 millimeters. With the pilot hole in place, it is now time to bring out the long series drill. Due to the excessive length of this tool, the speed must remain under 500 RPM until the tip of the drill is submerged and into the pilot hole, as centrifugal force would cause the drill to break if it spins up to full RPM without the support of the pilot hole. As the long series drill enters the pilot hole, an MO4 command must be used to rotate anti-clockwise. This is to ensure the cutting edge does not snag on the edge of the pilot hole on entry. Once the long series drill is submerged into the pilot hole, the spindle then stops, before spinning up clockwise to full RPM. Through coolant then comes on, and the drill feeds straight through the material. The spindle speed is 6,968 RPM with a feed per revolution of 0.2 millimeters. As this long series drill drives through the material, there are two key fundamentals that are critical. The first being through coolant. High pressure through coolant is paramount, as it is effectively used to flush chips and prevent overheating. All coolant pressure must be directed to the tip of the tool and the tip of the tool only. Required coolant pressure can vary depending on the drill diameter, length-to-diameter ratio, and the type of material that you are drilling, so it's best to consult your tool manufacturer for their recommended coolant pressure. The second is adequate feed per revolution. It is human nature to slow the feed rate down to be on the safe side. However, feed per revolution plays a big part in breaking the chip and forcing the swarf to exit out the back of the hole. If the feed per revolution is too low, the swarf will not chip and as a result wrap around the drill, causing it to break. So there you have it, CAMAssist and our skilled machinist working together as a perfect hybrid. The AI is doing the legwork, providing the bulk of the program, which allows our skilled machinist to make better use of his time, meaning he can now focus on implementing more intricate strategies to tackle more challenging features. Give CAMAssist a try, download it today.